Hello, physicists. Mr. Kirsten here. We're going to be talking about Chapter 5 a little bit today, circular motion. So this is going to be a little different from some of the other lectures where we just do example problems. We're actually going to talk about some of the ideas here. So let's get around to talking about circular motion to start Chapter 5 here. This is what we're going to be doing, talking about circular motion, the kinematics, or just explaining the motion of it, and also explaining the dynamics of it. And a few other things we'll be doing in Chapter 5. Okay, here is the big idea. Uniform circular motion. What is it? Motion in a circle of constant radius at a constant speed. So, if you're spinning a ball on a string, right? The ball is moving in a circle. The radius of that circle is staying the same. Our speed is constant, but then our velocity is constantly changing because the direction of our motion is changing. But in uniform circular motion, the velocity vector is always tangent to your circle. So that's uniform circular motion. Okay, so on page 107 of your textbook, the author goes through a derivation about how you calculate centripetal acceleration. And the end result of the derivation is this. If you're traveling in a circular path of radius r and speed v, the magnitude of your centripetal or center-seeking acceleration is v squared over r. You'll notice this is one of the equations on your equation sheet for the AP exam. So this is a big equation. Well, let's see if we can get an idea of the direction of motion here. Imagining I'm traveling in a circle, all right, and at some point in time 1, I have a velocity that's this way, like vector v1 here, and then at some point it's this way, vector v2. Well, what would my change in velocity be? Well, my change in velocity would be vector v2 minus v1, and that vector would be delta v here. Now notice the vector delta v is pointing towards the center of the circle, and that's actually what the word centripetal means. It's an acceleration that points an object, and an acceleration pointed towards the center of a circle. It actually means center seeking. So if you're moving in a circle, you're always accelerating towards the center. And the magnitude of that acceleration is your speed squared divided by your radius. Okay? So that's kind of the big idea for uniform circular motion. Notice no matter where you are at on the circle, if you're moving in uniform circular motion, your acceleration is perpendicular to your velocity. So the velocity is always tangent, and then the acceleration is always pointing towards the center. So you maintain this nice 90-degree angle here. Note here this acceleration towards the center of the circle, it's called centripetal. Some people mispronounce that centrifugal, which is a force in a non-inertial reference frame. But we're gonna mostly use the term centripetal, meaning center-seeking acceleration. Sometimes they say radial, meaning an acceleration along a radius. So anyway, centripetal acceleration is what we're talking about. Okay, so then if you're accelerating towards the center of a circle, it would make sense that there must be a force pulling you towards the center. And we call that force a centripetal force or a radial force. And the magnitude of that force, well, if we know our centripetal acceleration, a centripetal force would have to be mass times acceleration by Newton's second law. So here we have a formula for the force needed to keep an object of mass m moving at speed v in a radius of circle r. This is our formula for centripetal acceleration, centripetal force, mass times centripetal acceleration. I mean, you can kind of imagine if you're twirling a ball on a string here. You have to be pulling in on the string to get the object to keep moving in a circular path. And again, here's just another diagram here, thinking about what's going on here, that you're pulling inward to keep the object moving in a circular path. Well, what if this string were to suddenly break? What would happen? Well, as soon as we no longer have that centripetal force, we would start moving in a straight line. Remember, to move along a curved path, something has to be accelerating you and changing your direction. As soon as you no longer have a centripetal force, you would continue to move in a straight line. So yes, note this does not happen, right? When you stop, when your centripetal force is no longer there, you simply would move in a straight line. If your centripetal force vanishes, your object will fly off on tangents. Speaking of flying off on tangents, that's something your physics teacher often does. Okay. So how do you drive your car? How do you get your car to turn? Well, when you're turning and along a nice constant curve, your tires provide a centripetal force through their interaction with the ground, the road. It's a friction force that supplies the force you need to turn your car. So if the road is flat, and you're going along a turn, it's the force of friction between your tires and the car that provides the centripetal force needed to move you along a curved path. Now, if you're at racetracks, you might notice something like this. A car goes around a curve, right? But they're going too fast, and the tires start to skid, and there's not enough friction to provide a centripetal force and keep you going in a curve. So instead of moving in a curve with no friction, you'd move in a straight line, which we all know would be bad. And there's a couple things that happen if a race car starts to skid in a turn. Number one, even though the car is moving, since the tires are spinning, you're actually dealing with static friction. That is, one point on the tire always stays on the same point on the road. So even though the tires are moving, as long as you're not skidding, you're dealing with static friction. Now, if your tires start to slip, like if you're peeling out or you're going around a corner and the tires start to slip, you're then dealing with kinetic friction because the tire's sliding over the road surface. So basically, if you start to skid, you start in kinetic friction, which is smaller than static friction, which means you have even less control. Anyway, race cars, it's not very often that when you start to skid in the middle of a turn that you recover. So one way racetracks deal with trying to get cars a little more ability to turn is they bank their turns. All right. So as they're coming around the corner will be banked. Lots of physics going on there. We'll talk about this a little more later. Final thing in the lecture for today. So, a centrifuge is a device that works by spinning objects very fast and provides a large centripetal force. Centrifuges is how you can get blood plasma out of blood and all sorts of different things. So anyway, there's some problems you'll have in your homework about centrifuges that are kind of interesting. Okay, so I'm going to pause for just a quick second here, and we'll get the Elmo set up, and we'll do a sample problem from homework 5.1 here. Just a quick pause here.